recording. So as you know, we are now in week 4 and we are reviewing week 3. Week 3 starts with limits and limit laws. Today I will have time to go over at least 2 units of this week, which will be basically limit laws and squeeze theorem. And we will do some examples for that. Next session on Wednesday, we will do the other 2 parts. Very quickly, what is limit? Okay, so far we had this evaluation of function that we understand what is going on. So if you have a point, you evaluate it and get the value of the function. Ooh, sorry, I should change all these things earlier. Yes, so that's the value of the function at a. When it comes to limit, this is a little bit different story. Limit is studying the trend of the values of function when we get closer to a. So when you write limit of function as x approaches to a, what we really mean is not value of function at a. It might be the same as the value of the function at a, but what we really mean is that what is the trend of values of function at numbers at inputs very close to a. So well, there is a very precise definition of limit which we won't cover in this function in this course, but it mathematically it can be made sense very precise. What happens is that we go around this point and we try to see as we get closer to a, so the values, different values, we study the values of function when we get closer to a, so from both sides. And then while we see that as we get closer to a, the values of function gets to something. That something, if there is such a thing, is called limit of the function f at a. One big thing for you to understand is that value evaluation and limit of function at the same point, like limit of function as x goes to a and value of function at a, these two are completely different things. I'm not, okay, I should not write not equal. These are different notions. They may turn out to be the same in some cases, in good cases, but in general, when we study value of the function, we study only value of function at one point. When we study limit of function as x goes to a, we don't consider value of the function at a, but the trend of values of function as the inputs getting closer and closer to it. So you have to make sure that you understand these two and you see the difference between these. Well, I believe that you have watched videos and have gone through some basic examples. There are a precise way of making sense of that. But all those things will turn out for us at the end as a toolbox of facts, theorems, that we can use to evaluate the limits. So we are trying to make a toolbox of finding limits. Well, toolbox in math means theorems and well, facts and propositions, all those things. One and very beginning one is taking care of tons of very basic and very frequent functions that we know. This is starting with two nice functions. When our function is x itself, it means that here the function is f of x is equal to x. Whatever you input spits out. This, the limit is a, limit of the constant is constant, no matter where x goes to. So these are two easy to understand. Why are these things true? But then after that, we have this operation. So if you have two functions, you add them, and you know that each one of these guys have limit as x goes to a, then you can find the limits one by one and then add them. So limit and sum works nicely together. Well, this is the same thing when you have subtraction. It's the same thing when you have product. And I'll leave that one there as is. So limit of product is product limit. Sum of limits, limit of sums is sums of limits, and the difference goes the same. There is the third case that you may say that, okay, so then most probably we have this case also true. This quotient law, that's the name. But quotient law, we have to be very careful. This guy can turn out to be equal to 0, and we don't like to have 0 in the denominator. So this is only true if this guy exists and it's not equal to 0. So all four operations work nicely with limit. There's only one case that you have to make sure that you understand, you separate it, and that's when the quotient comes in, and you have the quotient of when you're finding limit of quotient, you have to make sure that the denominator is not equal to 0. When it's equal to 0, that's a story that we will cover later, but that's one. There is then a power law, which says that for any function, when you have to the power n as x goes to a, this will be limit of the function as x goes to a. And while the nth root is other version of this, which is saying the limit of nth root of the function as x goes to a is nth root of limit of function as x goes to a. Yes, there are some technical conditions here, but one is that I am assuming all these cases, limit of x as a limit of function and limit of the other function g exist. So if they don't exist, you cannot use these properties. Well, to start, this is the big toolbox that we are going to use. The limit laws. These are called limit laws. And I'm just going to do some examples for this one. Is there any questions, any comments before I go to the examples? Okay, here I have two functions, f and g, and I know that the limit at 1 and 2 for these two functions exists, and it's a number. Now, it's asking to find what's the limit of function f of x plus 3g of x. Since I know that both of them have a limit at 1 or as x approaches to 1, we can use some law, and that will give me limit of function as x goes to 1 plus limit of 3 g of x as x goes to 1. And then for this guy, I can apply the product law and write it as limit of function as x approaches to 1 plus limit of constant times limit of g as x goes to 1 as x goes to 1. And then use the facts given. Function, the f function, the limit at 1 is 1 plus 3 times limit of function g as x approaches to 1 is 0. So I have 1 for this. You can apply the same kind of rules, what different set. I will just write it very fast for this one. Limit of f, limit of g, then squared plus limit of 1 as x approaches to 1 as x, 2, here's 2 and here's 2, and that will give me as x approaches to 2, this is -3, as x approaches to the g gives me the limit 2 squared plus 1, that is -12 plus 1, which is -11. Rihanna, yes, please.
If we were on if we were doing a test and you gave us like a question like this, do we have to like show like how we derived it with like the limit f of x as x approaches 2, like when we're trying to solve it, could we just do like the last line and we'd get the same marks?
Like do this one.
Yeah,
like this.
like if we did
I wouldn't suggest that. Are you in hurry to get the full mark? That's a question, yes? You asked me a question, I'm asking you a question. Are you in hurry to get full mark?
Yeah.
Then try to put at least 1 or 2 steps.
Okay.
That's more like that way you will be more confident that, oh, I'm doing everything right. And I'm showing that I know how I'm getting this.
Okay, sounds good. Thank you.
Yes, as in the assignments as well, we are interested in seeing what is the final answer for the questions, but we are not only interested in the final answer. We want you to show your work, and the bare minimum for such limit is this bare minimum. So I can do like tens of extra steps like this, which will be appreciated if you do that, but for this one, I would say, okay, put at least some steps so that if you make a mistake in middle parts, at least you will get partial mark for those ones. Let me do one more. Limit of x squared minus gx over 1 plus x gx. So this is quotient. When it comes to the quotient, Rihanna, do you still have question or? Okay, thank you. So when you have quotient, you have to make sure that the limit of the denominator is non-zero to be able to apply quotient law. Well, there are other ways if the quotient is 0, but if you want to use quotient law, you have to make sure that the limit of the denominator, which in this case 1 plus 1 times limit of gx as x goes to 1 is 0. So this is 1 plus 0, which is 1. Since the limit of the denominator is non-zero, I can go ahead and use quotient law. Quotient law says that just compute the limit of the numerator and compute the limit of the denominator, and then divide them. So in this case, this will be limit of x squared, x goes to 1, minus limit of f of x as x goes to 1. We already computed the limit of the denominator, well, the other one, which was 1. So I have 1 squared minus limit of f of x as x goes to 1 is 1, 1. So 1 squared minus 1 is 0 over 1, which will give me limit 0. So just show some steps and show that you understand what's going on. I will leave this one for you to do it yourself. Before I move to the next question, next problem, please ask if you have any questions. Well, the basic limits can also appear in more nicer way, like this one. I can now try to evaluate this limit. Okay, I see that I have to first use the sum and difference law, then power, then product, but I will write it in one step for you that, okay, so this is power law. Then this is product law, and this whole thing is sum and difference law. So that will give me 1 cube minus 4 times 1 plus 1, and that will give me 1 minus 4 plus 1, which is negative 2. Same kind of work I can show here, but this is quotient. Before I start working with quotient, at least this is the process you have to make sure that you do whenever you get in the quotients. You first try to understand what is the limit of the denominator. I cannot use quotient law if the limit of the denominator is 0. So in this case, this will give me the limit of x squared minus limit of 3 limit of x as x goes to 2 as x goes to 2 plus limit of 5 as x goes to 2. And my handwriting is awful, and it evolves to even more awful handwriting. I apologize for that. I hope that by this point now you're an expert of reading my handwritings. 4 minus 6 plus 5, that will give me 3. This is not equal to 0, so that will mean that, oh, right away, this is, I can use the quotient law, and this will give me limit of x minus 1 as x goes to 1 over limit of this guy as x goes to, oh, sorry, as x goes to 2. And that is 2 minus 1. And I found the denominator 3. This is 1 over 3. This part is, this third example is easy to do because when you work with this guy, you will notice that, oh, this part is not very difficult, because if I apply the power or root law, this will give me limit of x to the power 3 minus x squared plus 3 as x goes to 0. This is a second root of limit of x goes to 0. And well, by the very general observations that we have been doing here, I can say that, oh, this is 0 cubed minus 0 squared plus 3, and that's root 3. That's good. How about cosine theta? Cosine theta, find the limit of cosine of x, sorry, as x goes to 0. this is not something that we can do right away, but just intuitively, you know the graph of cosine x. This is what cosine x looks like. And as we get closer to zero, when I'm trying to find a limit of cosine x as x goes to zero, I'm not interested in the value of cosine at zero. I'm interested in what happens when we get closer to zero. And well, here's what happens. As we get closer, the values get closer to, well, from both sides actually. Both sides, the values of y gets closer to 1. So this is actually 1. In general, you will see that limit of cosine of x as x approaches to a is indeed cosine of a. Well, that's how we will see there. So this will be just 1 times √3. This is √3. I have done this one, I have done this one, and as a result of those ones, we have that. This last example, this is an interesting example. Well, when I try to look at this function, absolute value of x plus 1 over x plus 1. I know that absolute value of x is, well, if x is positive, this will be just x itself. If x is negative, I have to multiply it by a negative sign. Now, instead of x, I have x plus 1. Absolute value of x plus 1 then would be, it will be x plus 1 if x plus 1 is bigger than or equal to 0. But that's the same thing as saying when x is bigger than equal to negative. When we have x plus 1 less than 0, this will be multiplied by the whole negative side. And here, well, what does this mean? This is basically x less than -1. This will be minus x. Now, I have absolute value of x divided by x, absolute value of x plus 1 divided by x plus 1. So I know what is absolute value of x plus 1. This is here. But then if I divide it by x plus 1, well, I have to be careful. Since I'm dividing it by x plus 1, I'm not allowed to put -1 there. So the function is not defined at -1. And here's x plus 1. But you can simplify these guys. And while x plus 1 over x plus 1 is 1, minus x minus 1 over x plus 1 is negative. You know what? I should have done different order these things. I should have done this one first, and then write it this one on the right hand side. You never know what will happen to your writings as you go on. This is interesting. Yes, so that way, then you have the function. Function is there, and you can say that, okay, I have now the function. Look at the graph of this function. This function is an interesting function. And when you try to sketch this graph, first of all, at -1, it is not defined. And for anything bigger than -1, it's nothing but 1, constant function 1. For all the values less than -1, it is -1. That's the graph. Now, when I try to get closer to this function, they will give me different values if I decide to get closer from the right or from the left. If I get closer to -1 from the right, all I see is that, oh, these values are all constant 1. And that is denoted by this so-called one-sided limit. So the function here, as x goes to -1 from the right, that's how we say we are approaching to a number, approaching to -1 from the right-hand side, or from the numbers bigger than -1. This guy is equal to 1. But if I use the values of x, which are closer getting, which are less than -1, and I get closer to -1, what I notice that, oh, all these values are -1. In other words, limit of the function as x approaches to -1 from the left. This is what it means here. Approaching to -1 from the left-hand side. All these values are giving me -1. So from one side, you get closer to -1. From the other side, you get closer to 1. In general, you cannot say that these values are getting closer to one number. So in other words, the limit of this function, without considering which direction this x approaches to -1, this does not exist. And well, that's an example for us to start so-called a topic called a one-sided limit. And as you saw, when I say that limit of function as x approaches to a number from the right, it means that I'm just restricting myself to the right-hand side values of a, and from the left, it means that I'm getting closer to the a from the numbers less than a. Now, this is another tool into your toolbox. This is a theorem. It says that limit of a function as x approaches to a exists if and only if both one-sided limits exist and they are the same. So the limits, they are giving me numbers, also they have the same values. And in the previous example, we saw that if the right limit exists, the left limit exists, they're not equal, we concluded that the limit does not exist. That was just an easy example to see that, well, this theorem, which needs a little bit more work, is true. So this is very important tool for us, because now, if we know how to find one-sided limits, we can find one-sided limit of function as x approaches to a from right, from left separately. Sometimes those are easier to compute, and then compare the values. If the values are equal, then the limit exists and is equal to that number. If they are not equal, the function does not have a limit at that point. So that's the tool, which is very important, specifically when we are working with piecewise defined functions. So let me bring it down. This is very important tool. I'll put it inside the box. And you should remember that. Before I go to examples, any questions, any comments? Okay. So let me then do examples. This is specifically useful when we are trying to find the limit of a piecewise defined function. Where as x approaches to a separating point on the domain. By separating point, I mean this is the point at which the function the formula for the function changes. For example, in this example, look at this example, x equal to -1 and x equal to 0 are examples of separating point. As x approaches to these guys, we have to use that tool. Meaning what? Meaning that, okay, for example, if someone tells you find the limit of function as x approaches to -1, you start trying to get closer to -1, but numbers closer to -1 are included in both of these parts, you see? So that means that, are you going to use this formula or that formula? We can consider only one-sided limits, and that one-sided limits will restrict our domain, and we can use one of these formulas and get the value. For example, as x goes to -1 from the left, -1 from the left means that I am approaching to values of x. I'm approaching to -1, values of x which are less than -1. I'm getting closer to -1, but from the left. So that means that the formula that will work for our function in this case is x plus 2. But x plus 2 is a good guy. This is a polynomial, and we know that it has limit no matter from left or right you compute, and that limit will be the same as the limit of the function x plus 2 as x approaches to -1 from both sides. And that is 1 plus 2. This is some law, and that is limit of function as x approaches to -1 from the right. From the right, it means that we are considering values of x which are close to -1, but they are bigger than -1. Bigger than -1 are included here. So when I'm trying to find the limit of function as x approaches to -1 from the right, I have to use this formula. And while by quotient law, this will be just 1 squared. So -1 squared plus 1, -1 minus 1. That will be 2 over -2, which is negative. Very nice. We found that, and then you say that, okay, I found the right limit. I found the left limit as x approaches to -1. These are not equal. That will simply mean that the limit as x approaches to -1 does not exist. Yusuf, please.
Yeah, I think the first one is -1 plus 2, right?
Oh, you're right. You're right. You're right. Thank you. Yes, I made a mistake there. This is -1. I'm approaching to negative, and this will be 1. But okay, good. Still not equal, and the limit does not exist. But thank you. Thanks for pointing that out.
You're welcome.
Well, how about as x approaches to 0 from the left? From the left means that x's are less than 0. So I will take this one as the formula that works for me. And this will be, again, quotient law can be applied here. 0 squared plus 1 over 0 minus 1, which is -1. And as we go from the right, this guy, the formula for this function is sine of 1 over x. And now we have to see if the sine of 1 over x as x approaches to 0 from the right-hand side exists or not. Before I do that, Haseen has a question.
Yeah, so my question is, for the second limit among these examples, what would happen if you factored x minus 1 from the top?
The top one doesn't have factor x minus 1. X squared plus 1 doesn't have factor of x minus 1. This you can.
Oh, right. Yeah.
At least in real numbers. That's what I mean.
Yeah, no, that makes sense. Sorry, I made a mistake in my calculation.
Okay. Good. Okay, sine of 1 over x. This is an interesting function because, first of all, sine of 1 over x, I cannot put 0 in the denominator, so it's not defined at x equal to 0. But what happens is that 1 over x, when you send x to 1 over x, the interval 0 to 1 will be sent to the interval 1 to plus infinity. And the interval 1 to plus infinity will be sent to interval 0 to 1. So what does this do is that you know that the graph of sine x, yes, this is the sine x, the graph from both sides. Yeah. Now, from 1 is somewhere here, 1. From this point on, everything you have to squeeze it and put it somewhere on this interval. And the way this works, you can try the online tools to sketch this thing. This whole thing now, you have to squeeze it, well, not uniformly. It will, as we get closer to 0, it will be more squeezed, and that will be something like, and then starts going up and down very, 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 very fast, never stops. And then from that point on, it will be, yeah, something like this. And on the other hand, will be something like this. But as you see, as we get closer to this guy, from left or right, doesn't matter. It just starts doing crazy things. Doesn't get closer to anything, just oscillates between -1 and 1 and gets faster and faster, That's one of the typical things that you will see as what we say, this is oscillating case. This limit does not exist. So one of the one-sided limits does not exist right away. From that, you conclude that the whole limit does not exist. Okay, and that's one of the interesting cases that will be nice to see what is happening. Any questions, any comments before I move to the next example? Okay. I have some examples here. I will leave it for you to do it yourself. examples. Well, by the way, okay, interesting. I have the answers all there. But okay, this one. So you have to be able to look at the graph of functions and find the limit just by that intuitive way of looking at these graphs that I mentioned at the beginning. Also, you have to be able to use the limit laws. You have to be able to use this the last tool that I introduced. It's right and left limits. You can use to evaluate the limit, and if they're not equal, the whole limit does not exist. There is a third rule, there's a third tool, there's a third important theorem. It's called squeeze theorem. And that will give us another important tool to evaluate some limits. What does this say? This says that assume that we have three functions. Which are let functions, let f, g, h satisfy this inequality for values of x close to a, not including a. So when we get closer to point A, the function g, I don't know what is it, and I don't want to think about the value of the function at point A. The graph of the function h, actually, I should say h, at every point, the value of the function is bigger than value of the function g. So it means that the graph of this function g will be less than or always below this function h. And one more thing, the function f is also less than the function g. Okay, so that's the meaning of this guy in graphs. So in terms of graphs. Now, this is if this happens. And another thing, limit of the lower function and limit of the upper function exist, and they are the same. So this inequality is true, and the function, upper function and lower function has the same limit. What does it mean? It means that when we get closer to a, the values of these functions will get closer to the same number. So it means that they will kind of meet each other at that point. Now, if function g is between them, then from 1 and 2, the squeeze theorem, or what's called sandwich theorem sometimes, implies that the middle one has a limit and its limit is exactly the limit of the other two. Okay. Important things is that squeeze theorem is a car. It's a tool. It will start working if you have these two conditions for your functions. It's like, okay, so I have this drill. I want to make a hole in the wall. The first thing is that I have to plug this in the plugin, yes. And the second thing is that I have to push that button, otherwise it won't work. This is plug it in, this is push the button. If these two are there, then the drill will start working and it will make a hole in the wall. If any of these ones is not there, squeeze theorem cannot work. So you have to make sure to put all these steps when you're using squeeze theorem. First of all, you have to show me, or the grader or the person who's going to look at your solution, that the assumptions of the theorem is there, and then squeeze theorem starts working, and then you can get it. Well, here it means what? It means that one, you have to either find an inequality which has that format. Also, you have to be able to find the limits of two end functions, the biggest, the smallest one, and then from there you can go ahead and use the squeeze theorem. Most of the time, squeeze theorem is the difficult part of the squeeze theorem is finding this inequality. You have to find two functions which are less than your function. One is less than, the other one is bigger than. Also, they have the same limits. Let us do one famous example here. You see, it's interesting. Here, can I use product law? Can I use limit of x squared? I found limit of x squared, and then I found limit of cosine of 1 over x, and then multiply them. Can anyone answer that? Can I use product law for this limit, to find this limit? I am over time. Maybe that's why no one is answering. But give me that answer. 2 more minutes, we go. Can I use product law for this limit? Are you guys all there? Do you hear me? The product law cannot be applied. I will leave that for you to think about why this product law cannot be applied. But what I know is that I know that cosine of any number, anything that you take, is between 1 and -1. And if I multiply, well, that thing is specifically can be 1 over x, yes? Now, if you multiply both sides by x squared, so this will be x squared times -1. Remember, x squared is always positive number. So when you multiply, it's not going to change anything. Any part of inequality, the inequalities will look the same. So that means that, oh, I found two functions. This is the bigger function. This is the smaller function. And this is always true, in particular when we have 1 over x here. Okay, so I have now two functions. This is g. F is less than our function, and h is bigger than our function. That's our first step. I cannot put 0 there because there's 1 over x there. But then you know that limit of lower function as x goes to 0 is limit of minus x squared as x goes to 0, which is minus 0 squared, and that is 0. Limit of upper function is 0 squared, which is 0. This is the second part. The limit exists, the limit exists. These are the same thing. So I had this inequality, that's first. I had two ends have limit as x approaches to 0. Then I can use squeeze theorem and say that limit of the middle function as x approaches to 0 exists, and it's equal to the limit that we found for those functions. And that's how you use squeeze theorem. You have to make sure that you find two good functions, one bigger, one smaller than your function, and they have the same limits as x goes to the given number a. And then you can use the squeeze theorem, and it will give you the value. Yes, Hasim.
So the cosine function being 1 over x for the limit that we just did, like, shouldn't that normally just by itself cause us to not have a limit?
Exactly.
If it's 1 over x.
So what you're saying is that limit of cosine of 1 over x as x goes to 0 does not exist. That's true.
Yeah.
But it doesn't say anything about x squared times cosine of 1 over x. You see, if one function has limit at one point and the other function does not have limit at that point, you cannot say that the product does not have limit at that point.
Okay.
You cannot use product law. That's exactly why you cannot use product law, because for product law, you have to make sure both of them have a limit. But okay, you have a screw to open up, yes, to screw in. You don't, your screwdriver doesn't work. Doesn't mean that there is something wrong with that screw, yes? Product rule won't work because one of the functions does not have limit as x approaches 0. But doesn't mean that your screw has a problem. You have to find right tool to work with. In this case, right tool to work with is squeeze theorem.
Gotcha. Yeah, thank you. That makes sense. Yeah.
Okay, so let me pause recording here.